Nalin, and today I will be talking about key management for consumer use cases. So first, I guess to get started, let me motivate this problem. So 3 months ago, TC and I, we had the realization that Ethereum has improved a lot. It was actually very feasible or very interesting to try to build a payment solution and use it in the real world. So we had this idea for Dymo, and Dymo originally was an idea for a wallet where we would start extremely focused on just doing stablecoin payments correctly, and see how far we can push the ideal. See how far we could push the ideal UX of Ethereum payments. It was sort of an exploration of how much better Ethereum UX can be given rollups and a lot of the recent innovation in Ethereum. So the sort of primary thesis was that rollups and account abstraction have made Ethereum a lot better recently, and that is in 4 very particular ways. So the 4 ways that enable Dymo in particular are having fast and cheap transactions, and having flexible account logic. So in particular, this enables flexible keys as well as flexible fees. Today, I'll be talking specifically about how flexible keys enabled by account abstraction are very useful for secure self-custody. Yeah, so zooming out a bit more, I think one way you can frame cryptography more broadly is that it is this way to turn real-world problems into key management problems. So, you start with these complicated problems of coordination and trust, and then you turn them into like discrete lock assumptions on private-public key pairs. Then, you port these over to the real world, and then in the real world, your security is limited by how securely your keys can be stored or the like entropy of the human brain storing the password. So broadly for Ethereum wallets as well as cryptography in general, whether it's your ZooPass frogs or SSL on the internet, the security of real-world cryptography really strongly depends on how keys are stored and managed. So what's, I guess, like the abstract solution to the key management problem? On the one hand, with modern security best practices, we've seen that secrets should be device locked and ephemeral. But on the other hand, the real world is quite messy, and people, lose their devices all the time, phones break all the time, all of that. So there's this tension between security and practicality. We think there is sort of a 2-part solution to this, just as this is a 2-part problem. And we'll discuss how we think of solving this with device keys and pass keys in the particular case of Dymo. So first, device keys. So most modern phones and laptops have this notion of secure hardware nowadays. iPhone and Macs call it the secure enclave. On Android, this is called the Strongbox key store. And in essence, what this is like is something quite a lot like a ledger, but built into your hardware already. And under the hood, how the way it works is that at an API level, it's quite simple for an app. The app can request a private key to either encrypt, decrypt, or assign messages. What happens when you make this request to the system is that completely separate from the user space and app's memory and CPU, there is a separate hardware chip inside your device that will only let the outputs of the cryptography leave this chip, and only do so if you provide some secure authentication, that's either your Face ID or Touch ID, something of that sort. So what this means is that you are extremely secure from software level attacks, and at the sort of minimum, you have to make a firmware level attack to break into and get either malicious signatures or get the key itself out of the secure enclave. And then sort of independent of device keys, there is this notion of pass keys. So pass keys sort of outside of our context as well are this new way to sign into websites and apps without passwords. Under the hood, pass keys are just ECDSA public-private key pairs that a password manager creates and then manages for you. So when an app or a website requests you to log in, your browser will verify with your Touch ID, your user presence check, that you're there, and then it will sign a message authorizing your login to the app. So what we can do for our use case is that with account abstraction, we can use this login mechanism to instead sign transactions. So we can ask the passkey to sign a transaction and authenticate a user that way. So this would create a key pair that is managed by your password manager, synced across your devices if you want it to be encrypted end-to-end, whatever else your password manager wants to do to secure it. So now you put these two types of key together. With device keys, you get guarantees that are a lot like a ledger. Keys never exist in plain text. They're not extractable from the secure enclave, and you're very safe from software attack vectors on your device. And with passkeys, you get the peace of mind of like having a backup that is as secure as your cloud storage, your password manager, whatever you prefer. So we've talked about the properties these types of keys enable. The other part of the question is how we can use these on Ethereum. So with account abstraction, actually first a side note, there's these two curves. So on one side you have SecP56K1, which is what is natively supported and used for ECDSA on Ethereum and Bitcoin. And then sort of the rest of the world uses SecP56R1, or also known as P56. So device keys, pass keys, and pretty much everything else where you see ECDSA in web browsers depends on the usage of P56 signatures. So natively, Ethereum only supports SecP56K1, but with account abstraction, we can have arbitrary verification logic, and that means we can have verification logic for P56 signatures and device keys and pass keys. So let's talk a little bit more about that. We've built P56 Verifier, which is a Solidity implementation to verify P56 signatures on-chain. As far as I know, this is the first audited sort of production-ready way to verify signatures from device keys, pass keys, WebAuthn, all of these YubiKeys, all of these kinds of outside crypto keys on-chain. And if you're interested in learning more about this or using this, you can check out p56.eth.limo. We also have a blog post for more under-the-hood details of how it works. So the sort of final piece of the puzzle of how we use account abstraction is to answer this question of, what happens if you lose a device or, you sell your device. So in the old world of like Ethereum and Bitcoin EOAs, you had these like long-lived seed phrases and there was basically no way to migrate them. But with account abstraction, you can change the set of authorized keys on-chain for an account. So in practice, what this means for the user is quite something like a add or remove device. So what you get is something a lot like WhatsApp or Signal. Under the hood, this is like if technically this is like a one-of-n multi-sig where the keys are either pass keys or device keys, and backups and devices can be added or removed as you want. So very simple UX, no seed phrases, no exposed private keys, nothing of that sort. And yeah, you put both of these together, you get what we have currently in production with Dymo. You have add and remove device, and here on the screen I have two of my passkey backups as well as two of my independent devices securing my account. Yeah, and so if you're interested in checking out Dymo, you can scan this QR, and there's a way to sign in with ZooPass and get or claim an invite using your ZooPass ticket. And then we'll also be running a community booth at 1 p.m. today. But yeah, I'm happy to take questions.
Hello, great talk, thank you. What's next for the wallet? Do you have any roadmap plans, or what's left for the mainnet release? Thank you.
Sorry, could you repeat the question?
Yeah. What's the roadmap for the wallet? Yeah, roadmap. And what's left to releasing mainnet?
Oh, yeah, so the question was, what's the roadmap and when are we releasing to mainnet? So we are on mainnet. We have been live on mainnet for a couple weeks now, and everything's audited and all of that good stuff. So yeah, you can check it out and download Dymo today. Sorry.
Hey, Nolan, great talk. Yeah, I had two main questions. So first question is around how exactly do you think about things like batch verification? I saw like the P256 verifier has like 300K gas to verify, if I'm correct, like somewhere in that range. And then additionally, when you're looking at like a sustainable model for Dymo, do you envision it going down the path of something like Venmo, where like you accrue fees as a part of this pool, like for assets that are held on Dymo over time, or do you envision a different model?
Yeah. So two questions. So first one about so maybe let me answer the second part first. So the second question was about how we envision Dymo going forward and how we envision devices being or accounts being used. I think ideally it would be great if like accounts have like one passkey backup as well as one device at the very minimum, and we'll try to like encourage users to do that. Our sort of model is like crypto wallets are great at doing two things: holding assets, and that part we want to do extremely securely for there's a lot of users of USDT on Tron and sort of not very secure infrastructure holding a lot of money. So for those kinds of use cases, we envision Dymo to be a great product fit. But yeah, we're very open to ideas and curious to hear more. And sorry, what was the first question again?
Oh, batch verification for the
yes.
P256 proofs.
Right. So batch verification. Yeah. So there's two parts to it. So first, right now it costs us about 330K computation gas to do one verification on chain, and in the case of batch verification, you would have I guess a constant cost, which would still be around like 100K or something on that order, but for any number of signatures. So it's very interesting. So I think for one part, there are not enough signatures out there on P256 to justify batch verification at the moment. But I do think, yeah, long term, it makes a lot of sense. It will be an interesting challenge to figure out how we can do it in a way that does not introduce like proving latency or add like a pre-processing step for the user. So it's a very, very interesting figuring that out. But the other part of this is also that the 330K computation gas is sort of not the dominating factor in the actual transaction costs, because Dymo in particular is on L2, and we envision that most use cases for P256 signatures will be on layer 2s. So the bigger cost is the cold data, which is not affected much by batch verification.
Another question here, Sean.
I'm curious if you guys have considered at all what the workflow might look like if a user already had an AA wallet separately and wanted to use Dymo, or is that a use case that you're not thinking too much about right now?
Yeah, great question. So we have like a way to like this is a normal Ethereum address, so you can send and receive any assets to it. So that is definitely one way to migrate, if that's the intention. But yeah, I guess if the question is if you interoperate with other front ends or something of that sort, then yeah, that's I guess all our code is open source, so we'd love to see people do that.
Yeah, for context, the thought was just if I had an AA wallet and then I went into Dymo, and then Dymo can instantiate the passkey, and then I can authorize that passkey with Dymo with my existing AA wallet, as opposed to Dymo spinning up a new AA wallet for me. That was the context, but maybe we can talk afterwards.
Right. Yeah, I think the right way to do it might be to create like keys with limited spends, or keys that so just create keys that have separate keys that are app authorized. We have not implemented that yet, but yeah, we would be very interested. All our code is open source, so if people want to try using it, they can do this. Yeah.
Cool. Thanks.
Yeah.
I think we have time for one more question. I just wanted to see one of your slides again. You said any problem can be reduced to a key management problem, something like that. It was
I think this does not work.
oh, Progit.
Oh, what was the slide?
The one about problems can be reduced to key management problems with like in the beginning, I think.
This one.
That one. Yeah. The one after that.
Oh.
Yes, thank you. Cool. Thanks.
Sure.
Okay, thank you very much. Round of applause.
Get there.